Okay, hi guys. Okay, so we're still proceeding with our problems on the first two lessons that we have done with the goal of trying to perfect our understanding of the algebraic notation of matrices to see how we can use it in problem solving in a linear algebra. So the next problem that we're going to look at is the problem which is based on symmetric and anti-symmetric matrices. You see, so if you recall from our first and second lesson, we actually gave a definition of a symmetric and an anti-symmetric matrices. So though it's correct, there is another nice way of actually defining symmetric and anti-symmetric matrices, which is connected to the last operation that we looked at in our second lesson, which is that of the transpose. You see that? So it's easy to define a symmetric matrix and an anti-symmetric matrix using that operation. And the definition goes as follows. You see that? So a matrix A, which is an n by n matrix, which is meaning it's a square matrix. So a matrix A is said to be symmetric if and only if A and A transpose are the same. So you see, so if both A and A transpose are the same, then we say the matrix A, the square matrix A, is symmetric. You see. Then B, a matrix A, which is still a square matrix, is said to be antisymmetric if and only if A is equal to the negative A transpose. You see. So these are some a nice definition or a nice way of actually redefining a symmetric matrix and an anti-symmetric matrix. You see that? So now, having these definitions in mind, we have the following problem that we want to look at, which actually talks about these things. So the question that we want to look at is as follows. You see that? So given that A and B are square matrices of the same order, given that A and B are square matrices of the same order, and also that A is equals to B plus B transpose, prove that A is a symmetric matrix. You see, so this is the question that we want to look at. You are given these two matrices A and B, which are related to each other according to this given relationship. So now the question is, prove that if A is defined this way, then A is a symmetric matrix. So how can we prove that A is a symmetric matrix? You see that? So let's go and see how we can go about that. So to go about that, this is how we proceed. So what exactly are we required to prove? So we are required to prove that A is equals to A transpose, because that's what we mean when we say A is symmetric. So that's what we want. So now to go about proving this, now we'll look at what exactly is A transpose. According to the definition that is given, we see that A transpose is the same as saying B plus B transpose transposed. You see that? Then now, if you recall from the time when we discussed this operation of the transpose, we say that every time if you want the transpose of the sum, it is the sum of the transposes. So which means from this line, it follows that we have B transpose plus B transpose transpose. Then again, we know that the transpose of the transpose is the matrix back itself. So which means we'll have B transpose plus B. But again, we know that the addition operator of matrices is commutative, which means I can change the order here to get B plus B transpose. But B plus B transpose is actually A. You see that? So therefore, we can see now that A is equals to A transpose, and thus the assertion follows. You see? So this is how we get to prove these results that we have here. So yeah, that's the end of our second problem that we wanted to do together. So yeah, let's just end it here for now. So we'll see more problems in the next videos to follow. Otherwise, thank you for watching. Have a good day.